Welcome to another Hopper on 6502 video. This one is about the minimal runtime, and specifically, in case that wasn't obvious yet, it's about floating point. In the Hopper environment, floating point types are 4-byte IEEE types, and Hopper longs are also 4-byte types, signed integers. Why is this interesting? Well, because the Hopper is very much a stack-based virtual machine, and for efficiency on a small device like, like a 6502 or a Z80, the stack slots are always 2 bytes. They're always 16-bit stack slots. What does that mean? It means that longs and floats are reference types in the Hopper runtime. So they're like strings. They're managed on the heap. So it's quite tricky to make floats and longs be efficient in Hopper. In fact, I never had floats on the 6502 runtime. Like I wrote the previous version of the runtime last year, I never had floats working until recently. And the way I implemented it is by only implementing about 4 APIs for both floats and longs. So simple APIs, well, they're sort of internal, like create a new one, dispose one, clone it, make a copy, because we do copy on write in our garbage collection. So some internal APIs, just enough to be able to write the entire floating point library in longhand here in actual Hopper code. So, I mean, you can see division here. This is quite a lot of Hopper. So I just wanted to get floating point working at all on the 6502 in Hopper. And I like this kind of reference implementation in that it's easy to understand, easy to read, well structured. It's not cryptic. But the downside of that is obviously it's going to be incredibly slow because this is interpreted on a virtual machine on the 6502. But this has benefits as well, in that the only code that's sitting in the ROM on the machine is those 4 little APIs, and they're very similar for longs and for floats because they just basically they just do the object management on the heap. So that means that we don't waste space on the ROM, and I've been trying to keep the minimal runtime below 16K, so people with different kinds of architectures, like for example banked ROMs, can still have Hopper just in a 16K ROM. Anyhow, after my experience, before I did this, I knew nothing about floating point. Well, I knew of course I knew, but nothing about implementing floating point. So since then, I've learned a fair amount about the 4-byte IEEE format, and it was a really good exercise implementing it this way. So then what I did is I ported this all to 6502 assembly, and that has made it obviously a lot more efficient, and it's taken up some space on the ROM now. So I've chewed up about 2,300 bytes. So, just over 2K is now not just the float, but I also ported longs, because longs were the same. So if I right click on that, I'll go to it. Longs were also implemented in longhand. So there's the add for longs, for example, quite long-winded. And you could optionally say you didn't want longs and floats in your runtime on your 6502, and you could build a version of the runtime which doesn't include them. And then I added a new option, which is this. And it's on by default. So fast 6502 runtime. And if you do that, then all these long APIs are now implemented as system APIs in the ROM in 6502 assembly, rather than using these ones that were written in longhand in Hopper. So pros and cons. If you use this, you end up chewing up more of your ROM, but you end up with much faster code. If you're barely using longs or floats, like you're just using them to time your benchmark or something, so you're not really, you're making 3 or 4 calls to longs or floats, then it makes sense to use the ones, the minimal runtime versions that are written in Hopper, because all this code will not be compiled into your application. Only the code you use will get compiled into your application. And if it's not in a mission critical part or speed critical part of your program, then this is actually a good solution. So less use of your ROM and less code compiled into your program too. We still have one major type to get onto the 6502 runtime, which is dictionaries. And because we've got lists and records there, but we don't have dictionaries on that, on the device runtime yet. I had them there in the first version of the runtime last year, but I haven't done them yet in this version because they're quite big. Another thing that we could optimize in this version of the portable runtime is strings, because strings are also mostly in Hopper like this. And part of the reason is last year's version of the runtime was about 24K, and that included strings and dictionaries. And I've been trying really hard to avoid going over that 16K limit. So with conditional, like optional, choosing your features, and also writing a lot more of it in Hopper code, because the Hopper interpreter on the 6502 is a lot faster than it was last year. So this works much better than it would have worked last year. Anyhow, I've got a little bit of a demo. So Noel's Retro Lab, he's got this loop demo, which basically in BASIC, if you're using this benchmarking in BASIC, it basically tells you how long your loops are. But he's got times for BASIC on an awful lot of machines. So on a lot of platforms, he's got published times for how fast this benchmark is. Yeah, on a lot of different platforms. So that makes it kind of handy because much like BASIC, Hopper is interpreted. So BASIC gets tokenized, and then the tokens are interpreted. Hopper gets compiled into virtual machine instructions, and those get interpreted by the virtual machine on the runtime. So they're in the same class in terms of those kinds of languages. Anyhow, we'll build it. At the bottom of the screen, we can see we're building and all that. Let's go back to this version. And I'm turning the LED on and off. I'm toggling it in each of the major loops. So this 10 loops on and off, we should see it flash 5 times. And I've got 2 versions of the benchmark. So let's upload it. I'll press F5 and upload it to my 6502, successfully uploaded. This black area on the top right, it's a serial console. Control 5 to run it without breakpoints. So it's like release mode. And then we've got our light flashing. 1, 2, 3, 4, 5 here. Let's go. Right, so that's the first one done. And there we can see the time. And then the second one's running faster. And I'll explain why in a second. So that first one took 14 seconds, and that second one took just under 9 seconds. So what's the difference between them, right? Well, this benchmark, you can see the total here is 5,500,000, or actually it's, 500,500 when it adds up the total in this S, which is like an accumulator variable, which means you have to use a 32-bit type to do this, or a floating point type to do this. I should have written one in floating point. That'd be fun. Huh. Yeah, I should do that. I'll try that again later. Maybe I'll add a comment to the video on how the floating point went time-wise versus these. So, almost 15 seconds, almost 9 seconds, we'll do floating point. Anyway, most basic interpreters that are halfway decent will use a wide type for their numeric their default numeric type is just a generic numeric type. So it won't be limited to 16 bits, it'll be 32 bits. And they'll use it throughout, like for the indexes for the loops and for the accumulator, etc. So if you do that, you're using long types, which in Hopper is a reference type. So this is a reference type being used for all this. So it's pretty impressive that it's creating and destroying little objects, because there's copy on write over here. So every time you do one of these, it's creating a new object and updating it. Every time you increment J, it's, is it? Yeah, I think it is. That's J equals J plus 1. So that's a copy on write. So there's a lot of objects being created and disposed. So it's pretty amazing that it pulls it off in 14 seconds. And then the second version here takes advantage of the fact that we know that these loop variables are never going to go over 16 bits. So if the loop variables are 16 bits and the only copy on write that we're doing is this line here, then you can see is a hell of a lot faster if you're not using reference types. And also if you're using 16-bit types to do we only need 16-bit types. Now let's go and see how we compare. So flip back and see what they look like on Noel's bench. So this is a public list of all these machines that he's benchmarked. And, many of these are running a lot slower, like at, 1 megahertz or 2 megahertz, right? But a lot of them are not. There's a, IBM PC clone taking 34 seconds for this benchmark in BASIC. And again, these are in BASIC, which is running in an interpreter. So tokenizing your BASIC and then interpreting the tokens. Whereas I compile to bytecodes and then run my bytecodes on a virtual machine, which is essentially an interpreter as well. It's not native code. It's not a compiler. So it's in the same class. The RC2014 is a good comparison because that's running at just about 8 megahertz, but it's a Z80 again, and Z80 8 megahertz is like 4 megahertz, and mine's running at 8 megahertz. But these things down here are running at 28 megahertz, 18 megahertz, 28 megahertz, and they're in the same ballpark as us as well. And the one that says using integers here, that means using 16 bits, so that's cheating, even more than I'm cheating here. That's making the accumulator be an integer as well. So I'm getting pretty close to the speed of the integer ones, but I'm using a long for 32-bit type for an accumulator. Anyway, very happy with this, managing to get it into so I've managed to get it into 2.5K for both the long APIs and the float APIs. And we've still got about a K left over in our 16K ROM. Maybe I put some string APIs in there, make strings faster. And in terms of speed, on some of my benchmarks, it's dramatically faster. So longs are about 50 times as fast, 50, as when you're just interpreting the Hopper code. And floats are about 400 times as fast. So the float benchmarks are pretty impressive. Yeah. I have a lot of testing as well. Might not be, I do my development process. I have a lot of regression tests I run through. So this is one example. I've got it running experimental. There we go. So if I run this regression test here, it uploads it to the device. I'm running it in the monitor here, not in the debugger. And then it's running float math and then all those other tests. So if I run it in here, you'll see what they were. But it passed because otherwise it hangs if it doesn't pass. If it fails, it'll stop. So the float math and then all the other tests. So yeah, I do a lot of testing on the way as well. Anyhow, very happy with our floats, very happy with our longs. Maybe we'll do strings and dictionaries next. So thanks again for watching.